Thanks everybody for having me here. It's very, very nice. And I'm aware that I'm speaking to a room of nerds who probably understands mass timber even better than I do. So I'm going to try and get into some technical detail, and what I'm going to try and do is tell you a story about, first of all, the Rocket and Tiggerly building, because that may be of interest to you. It involves a very new technology, and then secondly, a story of adaptive transformation and how timber technology can help lead the revolution in that. So I have some 200 slides to go through, so I'll go quite fast. There may be time for questions. If there is not time for questions, please just approach me personally, and I'll be more than happy to share things with you. And suffice to say that this presentation that I'm going to give today about Rocket and Tiggerly is like the first presentation that anybody has seen on that. So if there are hiccups, well, I'm afraid sorry. I'll just quickly take you through, introduce our company. Our company is actually one of the newer brands of Perkins & Will, who I think you probably know quite well in this area. We do operate in many ways, every part of Perkins & Will, if you like, operates somewhat independently in terms of the way that we lead design, but we are coordinating very closely to share research and share skills. So when you want to work with us, you probably will also be working with Perkins & Will in Vancouver or Toronto or wherever else you are. But we're very well rehearsed at being engaged in sharing information and techniques. This is us at Schmidt and Lassen. This is a picture in Norway. We're actually a Danish firm. But in truth, we have worldwide offices. Well, we have offices in China and two in Denmark. But we've done projects worldwide of all different scales. Everything actually from industrial design, small family houses to 465,000 square meter master plans and clusters of buildings. And what I really want to do today is just talk to you about the first part, super tall timber, which is really based around this project that we have the pleasure of designing, which is called Rocket and Tiggerly, and it's based in Winterthur, which is just north of Zurich, near the Bodensee. The locality is very special. It was actually understood as a kind of a city within a city. It's like a rail town. And typical of these post-industrial rail towns, it's an area that was designed to be self-sufficient back in the day that it was built, and has a tremendous history of the technology of the era. In fact, it was a very high technology place hundreds of years ago when it was built. And part of an overall master plan that is at the same time self-sufficient, but what we plan to do is reintegrate it with the neighborhood. When we were asked to design the building, we were actually asked to adopt this kind of form here, a tower attached to a ring, a courtyard ring. Understanding that there are a number of different functions for this already presupposed, for many reasons, we decided to cut it up and turn it into a series of individual addresses. And that's partly because of the idea that you could technically optimize the different types of timber technologies that were involved in each construction. We have a very different kind of timber technology that deals with high-rise versus more traditional CLT systems that deal with the lower-rise systems. And it was able to allow a different kind of urbanistic permeability as well, and a different series of addresses that you could where you could understand, I live in this building, or I work in this building and shop in this building. So that it gave more, let's say, qualities to the local area by dividing it up. There's also a very strong program in this design about public space, and the valorization of that public space into things that are, for biodiversity or for health and activity. And it was very important that, timber technology is not just a way of building, but a kind of, if you like, a symbol of a progression in society towards a healthier global system and a healthier personal life. So part of the value of cutting these forms up and arranging them carefully in the way that we did is actually the idea that the solar permeability would improve, and you can see, next, oops, go back. You can see how this can allow you to plan the public space in different ways and put the more public or active things at the right times of the day and night. And it was important also that the tower really marked, if you like, the center square of the public space. And so you have some sort of hierarchy between the main public square and the more private square behind. So here you can see the notion of this sort of private square, and our idea was to link in or even re-establish an old traditional rail centre that tied in with some of the neighbourhood shopping facilities and healthcare facilities. And the idea that, you know, through this permeability you get this sense of the neighbourhood beyond. Looking at the different qualities that you could achieve in the terraces, just the understanding that the ability to provide different addresses means that you can program not just the outdoor space, but the interior space or the rooftop spaces in a different way to allow access and egress to different parts. And here we have the notion that, you know, really this is a building designed for manufacture and assembly, and also to many extents designed for adaptation and disassembly. And this is expressed in quite a sober, but I consider quite a beautiful way on the facade, where you can have these exceptions for double height spaces, inset loggia, etc., etc. And the way that this exterior structure is expressed on the interior, and the use of mass timber as an actual visual finish on the inside of the spaces is something very special, because I understand that in British Columbia right now you have a law that makes sure you clad on both sides. In this case, we're going 100 meters tall. In fact, in Switzerland now, since 2015, there's been no height limit on what you can build. And so we have been able to do this, but we're also able to expose the structural timber as a finished surface, which is quite beautiful, I think. Up above, 365-degree view apartments, which is quite nice. And here we go for the structure. So the interesting thing about this structure is it's not a kind of core and curtain wall type of tower. We start with an internal tube, which is a kind of lattice, and this lattice bears moment and shear as well as structural stability, much like a core would, but it's permeable, which makes a very big difference between this kind of timber technology and the traditional sort of concrete core towers. Then you've got a very special system of floor plates, and that will be described in great detail later on, but suffice to say that they also transfer the forces to an exterior lattice, and this is one of the rare tower systems that are actually a tube in a tube type system, and both lattices, internal and external, work against each other in order to provide structural depth for shear, if that makes any sense. So the way that we've designed the tower is kind of an expression of the qualities of that structure, and it's really leveraging the amount of permeability you can get within this tube-in-tube system. And within this, we started to think about, of course, design for manufacture and assembly, pre-made volumetric stackable interior bathroom pods, and given within the strictures of this system, understanding how those apartments can be laid out, and more importantly, how these apartments can be changed and switched over time, so that there's not just a play of the facade and a series of different qualities of spaces at the beginning, but this can actually change over time according to how the market shifts. So the ability to provide this sort of play on the facade of inset loggia and outset windows is really aided by this ability to flip apartment spaces around. And as we go through, you can understand the transformations that can be made even within the volume are not just on the plan, but also in a section as well. Again, the question is, how did we come to a point where we could design this level of quality and use this kind of system and still make that, because it is a very innovative system, still make that profitable for the investor or for the developer? And how did we go from a point here where there was a lot of built mass and we actually reduced the amount of built mass, but still were able to create a higher ROI predictability than more square meters? And that really is the story about how we've designed a system specifically to measure the qualities that are readable in design at an early stage, and test those design qualities against a return on investment which understands and measures those qualities. So this is very different to the way real estate is even and cost versus return on investment is even predicted. So this is a system called profiteroles, and it measures things like trees and planting and what apartments or windows can be able to appreciate this kind of addition, the growth of a tree cycle over time. It looks at the adaptability and flexibility of floor plates and systems and how that might return value as the market changes. And to avoid a situation that, adaptability is extraordinarily important in our market, because trends and demands are shifting so rapidly in this late stage economic system that we have of capitalism, that you have to be able to transform the uses and purposes of these buildings to stop them being demolished. Looking at the LCA, the comparative LCA of this system versus a steel and concrete system, we have the idea that we're both using less steel and concrete in foundations and structure, but we're also sequestering carbon to an extent. And when you add up using the LCA measurement tools, when you add up these systems, we end up decreasing still the amount of steel and concrete effect by being able to sequester carbon in this, and this is well below all of the standards, if you like, or the aspirations of the industry so far. So just to play a couple of videos here. Oops, this is very interesting. Sorry. I'm just going to try and go back and let this video happen. Oops, 1, 2. Let's go. Okay. So this is the engineer, Andrea Frangi, and his talk, and these are the kind of tests that are actually happening in the ETH Zurich as we speak. The system has been designed for deployment, so it's already being built in some circumstances, but we've managed to have an agreement with the investor that we're actually going to let the technology develop until the point where we actually start building. And this is looking at the main structural system. This is looking at the acoustics, and of course with timber, vibration, reverb time, acoustics are extremely important. And the way that the floor plate is built up is extremely interesting, both from a structural and from an acoustic point of view. Here we have a situation where you've got a triple layered system where there's insulation in between and a series of pedestals, if you like, separating one from another. And the interesting thing about having a mass timber or CLT base is the intense amount of flexibility and seismic resistance that you can get through this floor plate. Also regarding, oops, goodness me, I'm not very good at this, am I? Hang on, we'll try it again. I'm too happy to click. Okay. Also regarding fire resistance, speaking with the engineers and with the design team, we've noticed that, of course, you're probably aware that timber is actually better than steel in many cases. There's no catastrophic failures. It self-protects through charring. But also, if a fire occurs in the structure, they've verified the ability to actually cut back that charring and rebuild the system. So without, over 90 minutes, which is what's required for this building, if there is a fire, it's not a demolition scenario, it's just a repair and rebuild scenario, which is, to me, very interesting. In terms of construction over time, we're looking at about a little bit less than a week per floor for 6 people on site. And that's more or less the end of the story so far for Rocket and Tiggerly, but suffice to say we're working very closely with our Vancouver studio, Perkins & Will, with UBC Gateway. A very special project, I think, and one that uses a composite system, steel, concrete and timber, mass timber. And likewise for the BCIT, and shout out to Fast and Ep also, who are the engineers on this project. Okay, part 2. I'm almost on time. This part of the discussion is really about adaptive transformation, because first of all, we believe that history has been a little bit perverted for the last century or so. Most of construction has been transformed and locally built using local materials and skills, which has the ability to natively change as the demands change. And here you can see this is in Meteora in Greece, built not by architects or engineers but by monks. And this is the sort of let's say engineering structural idea from somebody who was considered to be a master builder, again neither architect nor engineer, Antoni Gaudi. And within this sort of framework you have the idea that there's the master builder and the craftspeople, and there's a bidirectional flow of information. So those who construct the building are as influential on the design decisions as the designer themselves. Interestingly, like in 1890, there was an interesting period of time for architecture and engineering. In 1890, the world's tallest cathedral was built. It was 161 meters tall. And 1 year later, the world's first skyscraper was built, and it came up to a lofty height of 42.5 meters tall, I think was the actual height. And it was this first skyscraper, it was heralded as the first skyscraper because it represented a structural system and a kind of pedagogy where the architect and the engineer were actually separate professions for the first time. And that was extremely successful. It almost became, the first viral in the building industry, where this kind of system of separating professions became extremely effective commercially. So between 1885 and 1920, there was already a large separation of disciplines. And that continues to today, where actually there are many more separations. The interesting thing about these separations is the base understanding that all of us as consultants, we're not strictly speaking building buildings. An architect is not a builder, and neither is an engineer, but we're actually producers of media. And that media is interesting because the drawings that we produce, or the models that we design, are in part a legal specification. It's a kind of contract, one between another. And the way that architects have developed to communicate versus engineers versus many of the other professions that we can call consultants, there's a kind of boundary between where one person's expertise lies and the next person's expertise starts, and that is mediated by the kinds of information that we send to each other. There's a difficulty in that kind of information. And that hinges on the concept that expertise is pretty much equals the ownership of risk. And that's expertise means many things, but in a commercial sense, that's the driving force behind the division of labor and the division of expertise. And it becomes infinitely more complex when we're taught in architecture school that this is what a project looks like, and the relationship between architecture owners and contractors. And actually, these are just the standard versions of contracts these days. And between every little red dot in this shows that there is a contract structure between each of these members of the ecosystem. And that is married with the kinds of media and the kinds of specifications, drawings and models that we produce. And so within the system, of course, the division of labour has done many fantastic things. One thing is that we, in our lifetime, would expect to do many, many more projects and touch many more things than Antoni Gaudi did in his lifetime. But the amount of involvement in each project goes down, and the ability to receive information back from the contractors, from the subcontractors, from the builders starts to diminish. And so what we get is some positives and negatives with this system, some efficiencies, reduced risk and global knowledge, but then we miss, I guess, a little bit of this local innovation and specificity that comes with the place-based making and local economy of each particular area. So in Denmark, what the previous slide just showed, the sorts of things that were common in that particular building ecology. And now you can see that the way that we build is somewhat standardized with the rest of the world. And there's a good reason for that, because the division of labor, when it comes down to the consultants and the professions, are much better at handling standards that are global, looking at global supply chains of commodity materials, and also very not good at doing adaptive transformation of existing structures, because the nuances that are existing within those existing structures provide some level of risk and non-controllability by the people who are specifying or designing for that circumstance. So our profession then has become streamlined for new build because of the standardization in practice, and we don't tend to have skills of going out and measuring and for adaptive transformation, especially if things are structurally going to change quite a lot. So this expertise that we have in our system it creates another problem insofar as the kind of loop of information that where craftspeople would influence the master builder, and master builder would negotiate with the craftspeople, has turned into a situation where the negotiation becomes an aspect of liability. We have a tender process where we don't know really who is going to build the building in the first place, so we can't design for that particular builder, and neither when we have good suggestions from the builders coming back, that tends to be more troublesome than helpful. And so there's this kind of litigation and liability danger, which is counteractive in some ways to innovation process, and that's been exacerbated by the notion of financial risk in our global economic system. So you have Bill Clinton, who released the Banks from the Glass-Steagall Act, which some say led to a catastrophic event and future catastrophes. And the upshot of that for the building industry is the idea that you have buildings that are designed to last a very long time. Engineering has, for the last 50 years, have over-spec'd buildings. And they're designed to last an average 500 years with regular maintenance, but the lifespans of these buildings are going right down because the market shifts are the things that are determining the lifespans of buildings, not the quality of build or the structural capacity in most cases. So then we have this fun little diagram, which is essentially, it's called the skyscraper index, and it just demonstrates that the world's tallest building was built either just before or during a major financial crisis, and I hope that's not the same for Rocket and Tiggerley, which is the world's tallest timber building. But it's fair to say that the economic boom-bust cycle is having increasing severity. There's also a notion that when economic shifts move so rapidly, then there's this relationship with the urban environment that can be somewhat catastrophic at times, and we have to start thinking about a building methodology, approach, and design that allows for adaptability in our urban fabric. And that's not just for new build, that's also for when we transform, how do we transform? It's worthwhile saying that, in many cases you've got what I call the London paradox, which is the idea that there's simultaneously a housing shortage crisis, while at the same time huge areas of London, for example, the same as with Toronto and Melbourne, where I'm from, huge areas that remain untenanted because the interesting thing about these financial crises is that people feel that it's more solid to invest in space as a token of an investment, and therefore it doesn't need to be tenanted to make money. And so all of these effects, all of these macroeconomic effects are leading to this situation where market forces and trends are the determinant of a lifespan of a building. And why is that problematic? Well, this is one of the reasons why it's problematic. And the idea that what we want to do is, one thing that I learned last year is that there's now more built stuff in terms of weight, built stuff from humans, than the weight of every natural living thing combined. So the technosphere has outweighed the biosphere. That happened last year, apparently. And then the question is, if that's not a terrible thing, then how can we make the technosphere work for the biosphere? And that leads to a discussion of circularity. It means, what we want to do is actually, just like that we've learned in circularity with materials, that we want to reuse and repair before we recycle and before we burn it or before we send it to landfill. There's a sort of hierarchy and order of the way that we should do things. Well, the same goes for building circularity. We should be managing space before we adapt. We should be transforming and adapting before we demolish. And if we need to take a building down, we should deconstruct and use the materials. But the very first thing that we should do as designers when a building is no longer able to be serviced in use is to transform. That's by far the lowest carbon way of operating. So there's a sort of falsity in the world of certifications right now, where with most certifications you don't have to even consider the value of the building that exists before you tear it down and build something green, and you can still get a LEED Platinum for that. So the notion is we can start with circularity and the notion of harvesting. So if you do need to deconstruct a building, of course there's systems out there which are intricately tied in with BIM. Building as Material Bank is one of them, to reclaim the materials that you have and cycle that back into the use value of a new building. There's also the idea of, when we do harvest those materials, how do we use material passports, which are I hope you know what they are. They're intricately tied with systems of BIM and designed for disassembly. So the idea that for every material and for every component, let's say if a column wants to remain a column or a door wants to remain a door, the performance characteristics, not just the material ingredients, should be invested back into the product in the first place through BIM, and then transferred when they are reused. That metadata for those objects and for those materials starts to get transferred into new buildings, so that we can use materials not at their lowest possible value but at their highest possible value. So that relates to the whole concept when we design new of design for disassembly. And there's, of course, you're probably the team of people who would know most about it in this country, the idea of platforms, or PDFMA, Platform Design for Manufacture and Assembly. And so I'm not going to labor that point because you probably all know it. But it's really just about the idea of when you deconstruct, how do you make these individual components of building reusable in many forms. So a hospital becomes a school becomes a residence becomes an office. And there are many different systems out there, including our own systems where we've done it in Denmark for mass timber. And this is a building that we've demonstrated already in use. Mezzanines are added on a daily basis, well, not a daily basis, but once or twice a year, a new mezzanine goes up, a building extends, the floor plate is changed, the partitions change, and this happens on a sort of baseline structural level. When we talk about carbon, because that's an important point. Okay, the previous slide said that, but in the point of 2050, it's predicted that 80% of what we have in the built environment is already existing today. which already draws a point for adaptive transformation. But within that 37% of carbon that's produced in the world is produced within our industry. And this becomes an important point to think about when we talk about the lifespan of buildings as to how much of that carbon share comes with embodied carbon. If, number one, only 20% will be built new, and if buildings are lifespans are getting shorter and therefore their equivalent embodied carbon is going up, then we should start to look at those typologies that are at risk of being demolished first. And within those typologies, understand that, you know, if I look at the city centre and we take approximately 3 office towers, then just my design for that, you're looking at 160 full lifetimes of the average American, which is about 8 times the average human being on the earth. And in that case, the embodied carbon story becomes more and more important for the future of our planet. So if we take this a step further and just understand that, okay, if that's true, that 20% will be built new and 80% will remain. Well, if we start to look at that in terms of carbon, because operating carbon, you know, the amount that a building uses over its lifespan, that only represents a small fraction of the entire urban fabric, because energy codes are getting better, which is a fantastic thing. But then to have that amount of operating carbon, you're not going to get that much of a change in terms of your total city output of operating carbon. Whereas if you improve the existing stock by 50%, then you can see that you reduce dramatically the amount of carbon. So energy retrofits are an increasingly important part of the political story and the global health story. So, that was a weird slide, sorry. So looking into adaptive transformation as a method, what we have to understand is that really, just like a human body, if something goes wrong, you don't just demolish it and start again. There is value in the existing, the corporeal aspects of what exists. And so if we look at, this is the Boston Seaport, this is World Trade Center, and it was the largest building in the world when it was built. This was not really designed for anything but warehousing and storage, really. And, you know, there is this story of risk that accompanies every transformation, and especially something like this. But when you consider what is in the bones of the structure and in the what is built right now, it offers a series of qualities that you would never get if you did actually demolish it and rebuild it. You have the beauty of the structure, the heights of the spaces, the volumes that exist. And so this surgery is really about making one typology transfer into another typology. And this is, I think, generally what adaptive transformation, as I discussed it, is all about. So it really starts to take the trope of surgery and prosthetics in a way. It's like the idea that if there is value in the building itself, what is the imagination of the designers, the engineers, and the architects is really all about leveraging on what the existing value is. So the idea of having these sort of prosthetics that allow you to expand and supplement spaces that you didn't otherwise have. The idea that actually the main point is to ask the question, what qualities exist in the space and how do you leverage from those qualities? And the idea that most buildings, multi-story buildings that are built between about the 50s and the early 2000s are somehow over-engineered both in foundations and structures. And the ability to build onto that is actually very much available to us, but more available in lightweight systems such as timber that are pre-manufacturable and able to be specified and pre-manufactured to a high degree offsite and then transported and assembled on top of existing structures to match the columns, etc. And so this is a project that's going up just outside of the centre of Toronto called Victory Silos, and the top 9 floors were able to be added because of mass timber. And there's a lot of details about this project, but we have limited time, so I'll just show you some nice pictures. And then the notion of, I've got 16 minutes left, so I'm going to use that time. No? Okay, I don't have 16 minutes left. I'm just looking at the counter here, so I thought, well, I'll take my time, you know. And the notion of the idea that, you know, what is the least we can do for greatest effect? Because it's not just a financial thing, but also a moral obligation for us to preserve what exists and leverage from that. So this is a co-working space that is able to flex around the growth and collapsation cycles of startups. I'm just going to cruise through. The notion of life support systems, this is a library where the HVAC system was not okay for the preservation of books. So instead of demolishing the building and wiring in a new HVAC system, we actually just built a building and plugged it in as a kind of life support system from the outside. That also allowed for larger spaces like rooms like this to be added also to the library. And this is a very special project where, you know, it was a series of, if you like, a demand from the client to build 2 towers, and the understanding that actually you could adapt one side of the site so that the existing high quality structure was preserved, and a fairly low quality structure with low ceiling heights was harvested for materials. Oops. And then the top part there being made of mass timber to leverage the height that you could get as opposed to building another tower. And the idea that the existing facade was also adaptively transformed to give a different quality of use inside the space. All of our projects are leveraging from the concept of publicizing space and democracy. And this democratic space is I think, in some ways materially made valuable by mass timber and timber solutions. The ability to put a tower in one of those places allowed us to give space back to the city and still be profitable, which allows us to achieve many other things, biodiversity, water handling, etc. So the last part of the talk is about, you know, really the comparison against new build and how adaptive transformation can be a much more powerful player in the market sector. One of the things that's happening is material prices are skyrocketing right now. And politics is understanding the value of adaptive transformation versus demolition and rebuild, both from a carbon and resilience aspect, but also in terms of the local economies that are stimulated by transformation versus the global economic cycle of pulling materials in from very far away. So the standard method of valuing, you know, what a site can give is, okay, here's a plot, there might be something on it, maybe not. But the architects and designers are often not part of this situation. So, you know, the square meters and the location becomes the return on investment driver. Whereas if you start to model design options, and then you can start to take the qualities of those design options and measure against those qualities, like I showed you before with Rocket and Tiggerly. And so when you take this notion of financial resilience into account, for any self-similar building, you should expect that the cost of transformation is lower because most of it's already there. But because our industries are so bad at analyzing and so in a way so badly educated for the notion of adaptive transformation, we're not really trained as architects or engineers to handle this. The margin of error is unreasonably high for adaptive transformation versus a very refined process that's in place for new build based around the construction technologies that we've pretty much grown up with. So the idea is to reduce the margin of error, and using a series of both analytical techniques but also BIM-based modeling construction techniques. This is what we're really invested in for the future. SHL and Perkins & Will have decided to really focus on the idea of demonstrating a return on investment and a collapsation of the risk profile based on analysis and modeling. So it's worthwhile saying that, okay, we have a button that's not really working. Damn, doesn't matter. Scanning techniques, and we're invested in construction simulations that handle the nuances of existing buildings and how materials get in there. Maybe some of the final slides here are really about the market potential for transformation, because when you look at new build, material costs are unavoidable, and now that commodities are experiencing shocks in the logistics and the costs of extraction and delivery, etc., the material cost part is becoming more and more unpredictable for new build, and the labor cost is already so refined and already such a small component of the delivery that business as usual is not business as usual anymore, and the only way you can reduce cost is by entering the black market either with labor or materials. So in comparison, the notion of transformation relies very much more on the labor component, right? That's the part that's providing this risk profile or the unpredictability of how much the end result is going to cost. But that's the part that if we work on more astutely, we can really collapse the labor cost, because there are, and this is a group of people that can help with that kind of revolution. And it's because we haven't really examined that side of things, and the ability to do design for manufacture and assembly off-site and use these analytics tools that we're developing ourselves to get those, pre-assembled pieces into the building, match the nuances of the existing structure, get the old mechanics out, and change the vertical transportation. Those are the main factors, really, with adaptive transformation that need addressing, and they're not insurmountable, they just need some work. So that's more or less the end of my story, and I hope that you are interested enough to ask me some questions when I get back on the floor. Thanks.